Okay, welcome everyone. So this is today's speaker is Hidde Fokkema. He's my PhD student from the University of Amsterdam, and his general research area is mathematical analysis of interpretability and explainable machine learning. Hidde has a background in mathematics, but also in physics and also in AI. So he's like very broadly oriented. So today's talk, I think, is very interesting. We have actually Hidde today and also the speaker next time. They are both going to talk about fundamental limitations of explainable AI. So I think that's very interesting and something that really comes, it's really a benefit of developing theories, that you can also see the limitations of what's possible. So Hidde, if you want to share your screen, please go ahead and start whenever you're ready.
Yes, thanks. We should be set up correctly now. Yeah, so thank you for the introduction, and also thanks for the opportunity to present this work here. So I'm going to be talking about attribution-based explanations and mostly about what they cannot do. So this is work based on a paper I wrote with Tim, of course, my supervisor, and with Rianne de Hidde, who's an assistant professor at the Free University here in Amsterdam as well. And so what we'll be talking about, so to sort of set everyone on the same level, I would firstly introduce what I mean by attribution methods and by counterfactual methods. Then I'll talk a little bit about recourse and robustness. So what do these terms actually mean in our work? Then I'll talk about what they cannot do. So I'll introduce the impossibility result. And then not all hope is lost. So I'll talk about some ways that you can get around it. And also at the end, we could have a small discussion of other ways of getting around it than that is discussed in the presentations, because it depends a bit on what setting you allow. So that's the plan for today. And I will also say, if there are any questions or remarks during the presentation, just try to stop me. I think I have enough time to go into these things. Okay, so let's get started. The attribution methods. What do I mean by this? Well, an attribution method in the terminology of explainable machine learning is a post hoc and local method, meaning we assume that we are given some model, some machine learning model, for example, a classifier, binary classifier that maps features to a probability score. And then an attribution method will only explain those parts or of the function that is relevant to that particular point. And the model is fixed, so we only can make explanations after the fact. So we cannot use the training of the model. And the attribution method will assign to each coordinate in your feature some weight to which it attributes some important score. And depending on what this score is, this explains how important that particular feature was to the classification or the decision or the outcome of that model. And this is sometimes, or this can be typically visualized by these bar plots, or in pictures you can have highlights of the areas in the pixel space, or with text you can highlight certain words that were attributed with either a negative or a positive score. And well, because you can highlight these things, that's why I think they're also popular, because they give nice pictures, and it's clear to communicate what is going on. So well, we can have a very simple example. If we assume that your model is linear, so your function is just a linear combination of the features, then an attribution could be you just communicate all the weights that were needed for this model and for each particular coordinate. This is a particular case where the attribution does not depend on the actual point because because of how this is set up. But in general, your attribution will depend on X. And most methods or commonly used methods will use some kind of linearization around X to come up with these weights. Because and if your model is linear, then the weights they have a very clear interpretation or can be very clearly used for such an attribution. So that's why if you linearize, you get weights. But not all attribution methods will work out like this, of course. A very well-known example is Lime, so which does use this local linear approximation style. So, oh, sorry, I saw that there was a question. So I think postdoc is a more general term to use for methods. So these are any methods that are built upon existing models. So you get given a machine learning model, and after the fact you come up with an explanation. And an attribution method is just a particular instantiation of a postdoc method. So I hope that clears that up. So then back to an example. So the Lime is a very well-known example of a postdoc local explanation that uses attributions. The authors of Lime have come up with a very particular way of constructing a linear approximation around the point you're analyzing. And then they use this linear model to come up with attributions for each feature. And then they also, if your data is tabular, then you can visualize these weights with these bar plots as shown before. And you can, you can do something similar for images and for text as well. And also, I think one more example, or one slide of examples for attribution methods, which are based on gradients. So this is another particular route you can take. You can either, you can use the information that is in the gradient to come up with attributions, and either you take the gradient as is, or you try to smooth it with smooth gradient does, or you take you use some other smoothing technique like integrated gradients, and then you can also get attribution methods. But these are all examples of attribution methods, so that's what I mean if I use that word. And then I also have to talk about counterfactual methods. So a counterfactual method or counterfactual explanation is just you tell the user or the point that you're analyzing, you find another point such that it is as close as possible to the original point, but the decision is flipped or changed. So especially in classification, there might be one class that is undesirable, and then you want to know what is the minimal amount of effort I have to do to change the decision, and that gives you an explanation. And a very particular example could be if you apply for a loan, your loan application gets rejected, and then a counterfactual explanation could be if your income would have been so much higher than it is now, then your loan application would have been accepted. And well, we can also express this mathematically. And I'll stay in a binary classification example where now, so we have some binary classification model. We are analyzing a particular point, a counterfactual point for this X is any point that minimizes the distance between the 2 points, but with the constraints that the classification is, the other class or the positive class. And then one of the insights that we had is that you can use counterfactual methods to come up with attributions as well, because you can just take the vector that is pointing from your instance to the counterfactual point as some form of attribution. So that is one way to go from counterfactuals to attributions. And now you can ask, so these are the two methods that we will be looking at. And the first property that we would like to talk about or would like to discuss is robustness. So robustness in our definitions, well, it can be summarized as saying like similar users should get similar explanations, and basically means that the explanation should be continuous. The attribution should be continuous, and this is this definition of robustness is found in other works of the literature. For example, I have some references here, Karami and Alvarez, Meles, and Jacola, and also I saw recently at AI Sets I saw some papers discussing it like this. I will admit that sometimes robustness especially in the Jacola paper, it means Lipschitz continuity. We only assume continuity, which is slightly weaker. But then if even continuity is not possible, then Lipschitz continuity is definitely not possible. So that would be that's why we chose to assume only continuity. And then I also talk about I will have to talk about recourse sensitivity. So this is basically for counterfactuals, we could come up with if we have a counterfactual method, we can come up with an attribution method. Now we would maybe want to go the other way around. Let's say we have an attribution method, then we would like to go, we would like to be able to interpret it as a counterfactual explanation. And this comes from the fact that if you listen sometimes to the way Lime or Shep or some other attribution methods are introduced or used in practice, then often the interpretation that is given to these scores is as some kind of risk measure. So that if the Lime attribution or Shep attribution is positive, that means that if you increase that score, that it's beneficial for the outcome, or if you decrease it, it has a negative impact on the outcome. And this motivates that whenever a user has or wants to use an explanation, they always have some kind of goal in mind that they want to use the explanation for. So either with this loan application example, you want to be able to use the explanation to get the loan that you want, or you want to be able to use the explanation to increase your credit score. Or one particular example that Tim had in real life is that if sometimes for some, maybe you have to renew your card at the library or for the public transport, and you have to upload a picture, and then the site will tell you, no, your picture is not correct. But it doesn't tell you what is not correct about the picture. So you want to be able, if you get this kind of feedback, so your input gets classified negative or denied, you want to be able to know, okay, what should I change then to get it to be accepted? So these are all motivations to talk about recourse or recourse sensitivity. And how do we want to, okay, so how do we formalize this for attribution methods? Well, we call an attribution method recourse sensitive if the user can, well, we say achieve a sufficient utility increase. So utility then measures like what kind of goal you have. So either a classification change or a sufficient increase of the score of the model when you start moving in the direction of the attribution. So we interpret the attribution really as a direction that you should move along. And if you move along this direction, the goal that you had in mind will be achieved. And again, a similar story, as I said, with the continuity. This is quite a weak requirement, or quite a weak form of recourse. Because again, if then this is not possible, then any stronger notion of recourse is also not possible, which makes our impossibility result stronger. I can also, well, I talked about utility increase. Maybe this is still a bit abstract, and I can give some particular examples. So we've seen many examples of this utility in the form of an undesirable classification. There's one particular class you want to be, and then the utility can be measured in just either being that class or not. And we assume that this then is represented in a model as being the positive class and not the negative class. Maybe the machine learning model doesn't classify, or it gives classifications, but gives certain scores. and this score it's better if the score is positive or high. So you want to measure some increase in your score. Often models will also output probabilities, and you can also try to measure how much you can increase or decrease this probability. And these can all be summarized in some utility function. And then we say that the change achieves sufficient utility if the utility achieves some threshold level tau. And then, well, a little bit more mathematically defined for the recourse sensitivity. So we first assume that we define some area around the point that is analyzed, that is achievable, because we cannot assume that from any point can move to any other point, because in real life, the features represent things that you have to change, and this is sometimes difficult, or you cannot change certain features in the same way or independently. So we need to define some area around the point X that is achievable, which you call A. Then we look at all the points in A that achieves a sufficient increase in utility. And then we call an attribution method recourse sensitive if for every point in the input space, you can find there's some positive value such that there's some positive value and some other point in this area of achievable points with sufficient utility increase such that the attribution points in the direction of that particular point. And only if there are actually points that are close enough and achieve this utility increase. Otherwise, we are fine with the attribution pointing anywhere, because well then there's sort of no point to pointing in a particular direction, so we let it be anything. So that's the mathematical definition of recourse sensitivity. And then in a particular example that I mentioned before, so let's say these are sort of abstract representations of what kind of picture you might upload to a site to be posted or to be printed on a card. Then on the left, you see a picture that gets accepted, and then the recourse is, and then the picture in the left-hand box, but on the right shows you the attribution that you will get with it. And this is well, even though the picture is already accepted, this attribution will point you further into the accepted class, because the red colors are positive, which will push the grayscale values up, which is lighter, and the blue is negative, which will push the grayscale pixels down to 0, which is darker, and the contrast increases, which means it will get accepted. In the rejected pictures, you see the opposite. So the contrast between the figure on the picture and the background is not sufficient enough for the model or for the particular use case. And in this case, the background is blue, meaning it will become, if you would follow that direction, it will become darker, and the person on the picture is colored or is attributed positively or red, which would push it to be lighter, meaning the contrast will increase. So this is a particular example where there is an attribution method that also allows the interpretation of a counterfactual or as a recourse sensitive attribution method. So that is the setting that we're in. So hopefully I explained that clear enough. And then what is the impossibility, or what is not possible? Well, what we show in the paper is that there is no attribution method that can always be robust and provide recourse to all points, meaning there's no universal attribution method achieving both goals for all the points considered. So specifically, so we can go to a specific example again, using the binary classification setting. We cannot find a of what it specifically means is that for any attribution method, I can give you a continuous function f that acts as a classifier on some task, such that the attribution that is given by the attribution method is either not recurse sensitive or not continuous at some point. So that is a specific example of binary classification. And in the paper, we generalize this to, well, more general utility functions and more restricted functions or input spaces. And also accounting for the fact that sometimes you might not be able to move in all the directions. So this achievable set that I was talking about before could be much more constrained in our setting. So what does the proof is actually, I can quickly give you a proof sketch of why this is the case. And the proof is actually not too difficult. So we can look at the particular function that represents a classification. So let's say this parabola or this squared function is what we use to classify certain points. And then meaning that if this function is negative, you get classified as the negative class. And if it's positive, then you get classified as the positive class. And then for an attribution method to be recurse sensitive, it has to do the following things. So in the area where it's negative, it has to point towards an area that is positive. But the size of the space where it's negative is set up in such a way that on a portion of this set, it has to point to the left, because that's the closest boundary point for which you will become positive. And on the other half of the set, it has to point to the right, or because that's the closest point on the boundary for that particular subset of the negative space. And this is represented with these L and R sets. And then you can make the following observation. Basically saying in math what I said before is that on the area where it's purely the left sets and there's no overlap, the attribution has to point to the left or has to be negative. The set on the set where it's purely the right set, it has to point to the right or be positive. And on the intersection of both, it has to be at least non-zero. It doesn't matter where it points, both sides are close enough for the attribution to, or for our definition to allow to point to either, but it cannot be zero. But if you constrain this, then this contradicts the intermediate value theorem, because any positive function that goes from negative to positive has to go through zero. It cannot jump, otherwise it's not positive. And thus either you lose continuity, so there will be a jump, or it will have to keep being negative or positive or become zero somewhere, and which means it's not recurse sensitive in the way we define recurse sensitivity. And this is actually basically what you need for the general case as well. You have to you can embed this example in higher dimensions and turn it around in such a way that also all the constraints are present.
Can you please give a recap for the recurse definition?
So intuitively, the recurse definition means that if there are points close enough, meaning close enough in what you define to be close enough, which we use this delta for in this case. If there are points that are close enough that achieve sufficient utility increase, in this case being you move towards the positive class, then the attribution has to point to a point that achieves this utility increase. So in this case, that means that on the left-hand side of the left part of the negative class, you have to point to the left, because that's the closest, those are the closest points that achieve this utility increase by becoming a point that is classified as something positive. And on the right-hand side, the attribution has to point towards the right by a similar reason. And then in the middle where they overlap, there's a choice. You can either point towards the negative side or to the positive side, but it has to point to a side and it cannot be 0.
Okay,
So
I
I hope
got it.
good. Hopefully that clears it up. Yeah, so that's the proof sketch. And as I said before, this is actually all you sort of need to know to generalize to all other cases. The main idea in all the proofs remain the same. And you can see this happening in real life, and the way this manifests for attribution methods is that either they become discontinuous. So there will be jumps in explanations that you can measure by inputting points that are close together, and you can see the explanations jumping around. Or this manifests in the way that you cannot assign this recourse interpretation to the attribution. So the attribution, the weights, they tell you something about how important the input is, but you cannot use these weights to change the inputs at least in a simple way to achieve the goal that you want to achieve. So you have to be careful. If you use the attribution methods, my takeaway is that you should have to be careful with interpreting what the scores actually mean. Okay, so that's the impossibility result.
Can I ask a question?
Yeah, of course.
Okay, so I'll show myself if I ask a question. Okay, so if I understand it correctly, and I might be misunderstand about it, I understand something like recourse is kind of, I need to have the ability to go to some direction to improve my result, right? My prediction, whatever. And consistency means that for local neighborhood, for like result should like maintain consistency, right? So
Yeah.
If I understand it correctly, there's some examples that cannot be changed or something like this, right? This is the impossibility, which not sounds impossible. I think it makes sense in some sort of way. Like there's some people I don't want to give them loan because I don't believe I don't know. Their situation is like they are stuck in.
Yeah, I mean that's
maybe now when I'm saying it, maybe it's not that. I don't know.
Well, I think that it's definitely a correct remark that there are sometimes points that you do not, or you cannot give an explanation to that allows for recourse. But this is measured in our setting, I would say, by looking at these achievability sets. So you can constrain the points that you're looking at and set it up in such a way that points that are too difficult to move towards the positive set, or points that have to put in too much effort to get their loans approved, that they will not get a recourse sensitive explanation. The setting that we have allows for that. The impossibility results, what it says is that if there are people that want to get a loan and both persons will be it will be achievable for them to change their vehicles in such a way that they get the loan, then you don't want these two people that on paper look very, very much the same to get wildly different explanations. And our setting says that can happen if you use attribution methods for this type of explanations.
And I try to rephrase my another way. If I have more than one direction that I can go, they somehow can balance each other, right? To zeroing each other.
Yeah, that's basically the mechanism that
that
ensures that this is that you get this impossibility.
Yes.
And later on,
cool.
Okay, but later on in the discussion, actually, I will go into this interpretation a little bit more, and this maybe also allows you for a way out, actually.
I have a question.
Yeah, of course.
Do we want the explanation to be robust? Because maybe near the borderline, we want completely different explanations if we are given alone and if we're deciding not to give alone.
Yeah, so along the decision boundary, I can agree that you sometimes want very different explanations, but the result shows that this actually doesn't happen along the decision boundary, but sometimes quite far outside of the decision boundary. So in the example, for example, in this proof sketch, the points that risk not being continuous are the points that are right in the middle. So those are all the points that you can either choose to go left to the right, but they're not close to the decision boundary themselves.
Interesting. So even if you had a different definition of robustness, not the explanation entirely is continuous, but even inside each class, your proof will still hold. So you have a stronger result, right?
What do you mean by being another type of continuity or robustness?
I'm saying, what if we change the definition of robust explanation, and we won't require that the explanation is robust everywhere, but conditioned on the class. So in the class of -1, it's robust, and on the class of +1, it's robust.
Oh yeah. That I think the proof would still hold in that case. Yeah.
Cool. So
Yeah,
it's
it's
even
really
stronger.
it happens on the interior of these classes or these sets.
Mhm. Thanks.
Okay. Thanks for the questions. But like well, so this is the setting in which things cannot happen. But as you can see, the way the result is phrased, it doesn't mean that things always go wrong. There are particular functions for which attributions could still be both continuous or robust and recurse sensitive. And again, I can have an example from binary classification. The attributions can still have both properties if, for example, the preferred class that you have, so the positive class, if the set of points that achieve this classification is convex, then you can have an attribution that is recurse sensitive and robust by simply projecting onto the set. So convexity will give you that you have a unique a projection, and that this projection is also continuous. And then you can just look at the difference between the projection and the original point, and this is exactly the vector pointing towards your set of points that is positive. So this gives you an attribution that is both recurse sensitive and robust. So that's the observation that someone else made, and then you can generalize this result to more, well, we try to generalize this result to more general utility functions. The only problem is then the set that you want to project onto is dependent on which point you're analyzing. So it could change for any point that you want to build an attribution for. So that means you need for this projection to still be continuous, you need some continuous notion of these sets. And this exists, but I will not go into detail for it, but it's called hemi-continuity. And this is enough for us, or for the result to for us to prove that there are projections onto these sets that are continuous. And then you also need that these projections are that they exist, of course, and that they are unique. And then both will give you that these attributions are robust, and by definition of being projections onto the sets of points that are achieving enough utility, you can show that this is then also recurse sensitive. So that's a way of working around it. I said I wouldn't go into it. I think I'll skip this because it's not that important. And this is basically what I said before, but then in more math terms. So if you have this set continuity and all the projections that you have are unique and exist, then looking at this particular attribution method or a map will give you a method that is robust and recurse sensitive. I think that's what I want to say about this for now. But this tells you that there are some cases for which you can construct these attribution methods that have both properties, but you have to be in a particular setting. And I think in general, it will be difficult to check beforehand that the function that you're looking at has both properties, meaning that this utility increase that you want to observe, that the sets of points that achieve this utility increase have these nice properties. Is on the one hand very difficult to check, and on the other hand, it's quite easy to break. It's not that hard to come up with examples for which even this attribution method doesn't work again. But at least it gives you a way out. And then I think I want to discuss a little bit what other ways you can come up with to work around the setting or work around this result by changing the setting a little bit. So the observation that we had is that these counterfactual methods are always recurse sensitive by definition of how they're constructed. And the robustness, it fails basically whenever there are situations where you have a choice. So there's multiple counterfactual explanations that will be equally valid. And then because you have to choose, and sometimes you cannot choose in a continuous manner, this breaks robustness. So the one sort of obvious way of working around this this problem is by allowing for set valued explanations. But then I think there are methods that do this, of course. Well, not of course, but there are methods that do this, luckily. But and then you can come up with a new robustness criterion for the set valued explanations, and you can typically show that this is that these methods then work fine. But then giving these set valued explanations, it's computationally probably quite hard. And if you give, or computationally, you just get a combinatorial explosion quite quickly, especially if the dimension is large. And this attribution interpretation is quickly lost, because if you have now multiple, so then if you turn it around, so each counterfactual explanation becomes an attribution, but then you have for each the coordinate in your point or feature, you have multiple weights, and these weights might contradict each other because they depend on what the others do. So this attribution interpretation is then lost, but at least the other properties are still saved. And I think one other possible workaround that I'd like to think a little bit more about is that you can sometimes either group certain features with each other and then combine them maybe in a specific way, or you can look at concepts hidden in your features. And then if you give attributions on either these higher level features, so where you take combinations of certain features in a particular way, or you group them or you map them to some concept and you attribute this particular concept, then you can maybe work around this whole problem and come up with attribution methods that have an attribution, have an interpretation as an attribution, because you can say this particular concept in the features that is hidden is so important for the outcome. You can give recourse, because you can say, I want to change this concept in the direction that I'm pointing towards. And if you have some notion of continuity or topology, you can still ensure that there's some robustness notion possible. The problem is that if you allow for combination of features to be attributed as well, you get the same problem as before. You get a combinatorial explosion of amount of possibilities. And what you allow to be concepts might be a little bit ambiguous. it's difficult to come up with rigorous definitions of concepts, or either if you have if you're very, in a setting where there are very clear concepts, then you might need human annotation to allow the machine to learn these concepts, which is costly. So there are other negative sides to it, but I think this is an interesting way of coming up with explanations in general. And if you have any other maybe suggestions, we can discuss it a little bit later, a little bit more. But I think
Last question.
yeah.
So I try to many of the problems in attributing in feature attribution methods is the correlations, semi-correlations, correlations, like mutual information when information is not orthogonal between feature, right? So, so many of those, the impossibility results in SHAP and those kind of methods. This is what they based on. But I'm not sure. I need to think about it. That this is exactly the problem here, right? This is what those possible workarounds offer, right? Kind of grouping features together to a linear separated groups, right? Interdependent. This is what you offer, if I understand correctly, but basically, and then you have.
Yes, sorry, continue.
So no, it's like if I understand it, so when it's the groups of the features are orthogonal, you have some sort of each one contributes in a different direction.
Yeah.
Right, something like this. So I ask if somehow it's the problem of correlation, semi-correlation.
I think allowing for grouping or combinations or mapping to concepts can help alleviate with this correlation problem. But I think it goes a little bit further as well, because in the example or the proof sketch that I gave with this parabola, the problem wasn't necessarily that because there's only one feature, so it doesn't have to do with correlation. But when the impossibility shows up, it's because at some point in the space you have a choice between left and right. And here the relevant concept would be just move in any value, like take the norm of the absolute value of your feature and increase that. That will give you a valid explanation that is if you allow for a concept which is just the absolute value of your feature, there would be no impossibility result in that particular example. So I think the workaround suggested here goes a bit further than just correlations.
Okay, thanks.
I hope that answers your question a bit. Yeah, so I think that's all.
Hidde, I'm also wondering, maybe another workaround might be to look at a different sort of kind of explanations. That is, here you're considering unsigned explanations, right? Where each, basically the explanation is a direction in vector space. But what if what we consider as explanation is going to be a binary kind of vector, which only tells you whether like a feature is important or not, right? So from a low-end application perspective, I only aim to identify which feature I can change to kind of flip the decision of the resulting classifier. And what recourse would do is basically find the perturbation that's required for this particular feature to sort of change the decision. Do you think that might be a way to sort of avoid these impossibility results? That is, limit the scope of what we do with attributions in the first place.
So your suggestion would be, we don't tell you where to move, but if a feature needs to be changed for.
Yeah, like when we define feature attribution, what if we start with the definition saying that it doesn't tell you the direction, but it only tells you whether a feature is important or not. Like it's a binary vector.
I would think that would, at least from top of my head, I cannot come up with an example that goes wrong. So I think it would
Yeah, but I
definitely
think you
help.
will give up continuity then, right? If you ignore
Yeah,
the
you might not have a useful definition of continuity. Yeah.
Yeah, because
That's-
the output is a discrete in that case.
Yeah.
So yeah.
That's a fair point.
Sounds good. Thanks.
Okay, well, then I can briefly summarize what I've been telling then. Basically, the impossibility result that I presented is that says that for any attribution method that you come up with, there exists some continuous function for which that attribution will not be recurse sensitive and robust. There are still cases for which it is possible, but you need quite strong conditions, and these conditions might be difficult to check and are easily breakable. But yeah, sufficient conditions are possible. Yeah, hopefully we had a small discussion on when or how you can get around this result by changing the setup a little bit. In the paper, we have a couple of other generalizations of the result. First of all, we have a full characterization of when it is possible to have attributions that are recurse sensitive and robust. And the setting in general is quite general. So we allow a lot of constraints to be set on what the user can do, but then still impossibility results will pop up. That's that's it for my presentation, and thank you for your attention.
Yes, thank you, Hidde. I think there's time for questions. If yeah, let's maybe Hidde, maybe it's best to unshare your screen so we can.
Yeah. Well, if some people want to refer to a particular slide, then I'll put it back. But,
yes. Also stop the